Thanks, Zach, for the introduction and also for the invitation to speak today. As the title suggests, I'm going to be talking about model order reduction strategies for oscillatory dynamical systems. And the main result that I'm going to be talking about today is this adaptive reduction paradigm, which can allow for the implementation of larger inputs in reduced order models without sacrificing accuracy like you usually do for standard phase reduction strategies. I'm going to talk about a couple applications where this is useful and then give some concluding remarks. So the motivation, we're thinking about studying oscillatory dynamical systems in reduced order coordinate framework. And there's lots of applications in biology where oscillations can emerge. So for instance, this is a neuroscience conference, so we see oscillations in neurological rhythms. We also see oscillations in circadian cycles, where there's a 24-hour, approximately 24-hour period of oscillation so that you can entrain to a 24-hour light dark cycle. You have heart rhythms or arrhythmias, which can have oscillatory behaviors. So just in your mind, you can think about maybe a tonically firing neuron. So this is computational simulation data from a compartment-based tonically firing neuron. There are inner spike intervals, which are approximately the same from spike to spike, although there's some noise in the system. So it's not exactly the same, but these are the sorts of systems that we'd like to be able to understand in a reduced order coordinate framework without necessarily having to deal with state variables like ionic concentrations or gating variables or all sorts of other things. So to start out, there's a lot of different strategies that have been developed over the years for reduced order modeling of oscillations. I think one of the most elegant is that if you can find an invariant submanifold or an aggregate order parameter, so think like, for instance, the Kuramoto model and the Kuramoto order parameter, although there's been a lot of more recent instances of this, you can take a big population of oscillators and represent them with a couple ordinary differential equations. The trouble is that it's really difficult to find invariant submanifolds, so oftentimes you have to use other methods. Phase reduction is a really popular one in the neuroscience community, which was really developed by Winfrey in the 60s and also Ermintrout and Capel later on. More recently, Koopman-based methods have become popular, and Koopman operator theory says that you can represent any nonlinear dynamical system in terms of a linear but possibly infinite dimensional operator. And also phase amplitude-based methods have gained traction in recent years, where you take the phase coordinate and augment with an amplitude variable to get some of the information about the dynamics that are transverse to the periodic orbit. The strategy that I'm going to be talking about today is kind of a combination of these bottom three things. So just first, a little bit of background about model order reduction of oscillators. If you have an oscillatory dynamical system and you're interested in the timing of those oscillations, you can work in phase coordinates, which essentially say, or they encode for the timing of those oscillations. So you can define a phase, which ranges between 0 and 2 pi on a limit cycle, and you can scale it so that the time derivative of the phase is equal to a constant on that limit cycle. And then you can say, well, if I want to extend phase to the base of attractional limit cycle, I can use the notion of isochrones, which essentially say that if you start on the same isochrone, you're going to end up in the same spot in the limit as time goes to infinity. So in this slide, I'm showing a two-dimensional representation of Hodgkin-Huxley equations. We have voltage on the x-axis and a gating variable on the y-axis. This system has a stable periodic orbit, which I'm showing in gray here. And I'm plotting out all the isochrones for the system in various colors. And not surprisingly, if you take two initial conditions, one here and one here, on the same isochrone, if you integrate the behavior forward in time, they both approach the periodic orbit and they do so together. They end up in the same spot in the limit as time goes to infinity. Now, using this notion of phase, you can end up with a good reduction in the dimensionality using something called a phase reduction. So by restricting your attention to a very close proximity of that limit cycle, you can end up with dynamics for the phase variable that follow d theta dt is equal to that constant omega, the natural frequency, plus z of theta, which is the gradient of the phase evaluated on the periodic orbit, multiplied by an external input. So this is useful because it allows you to go from an n-dimensional system, where n could potentially be large, to a one-dimensional system where you're just thinking about the phase of oscillation close to that limit cycle. The problem with this is that you really only get a good picture of what's going on near the periodic orbit. If you have an input that kicks you into this region or this region here, standard phase reduction methods aren't going to be able to tell you what's going on, because you're going beyond that limit where the local linearization is a good approximation for the system dynamics. And so the big questions here, and a couple that I hope to give a decent answer in this talk, is how can we handle larger magnitude inputs? So for instance, to give us information about what's going on in here and what's going on here at the edges. And how can we do that without adding too many extra dimensions? And then also, what does this allow us to do that we couldn't do, say, simply using phase reduction methods that are working in the weakly perturbed paradigm? So this brings me to the main result that I want to talk about, which is this adaptive reduction paradigm, which is kind of an extension to standard phase reduction. So the main idea I'm going to describe on these next couple slides here. For the moment, we can think about, for concreteness, a three-dimensional model that's of gene regulation that's sometimes used to model circadian oscillations. So we have three variables, B, C, and D. Those describe the dynamics. And we have this term LC here, which you can think about it as a constant value of light input. So when the light input is 0 for this model, we get a stable limit cycle that emerges. It's showing here over in blue. And it's about 24 hours. If you take a look at a trace of the variable B for this periodic orbit, it's about 24 hours. That's a stable limit cycle. But for non-zero constant values of this light, we also have other periodic orbits that emerge in steady state. So a continuous family of periodic orbits is showing here as these black lines adjacent to this nominal blue periodic orbit. And as I mentioned previously, phase reduction starts to have problems if you push yourself out too far from a nominal limit cycle. So the idea here is maybe we could use this collection of periodic orbits to kind of adaptively update some nominal periodic orbits, so we'll stay at least close to one of those nominal limit cycles. The main idea behind that, as I'm showing on this slide, suppose you have, in this case, two discrete periodic orbits, one blue and one red, each which emerge for a different collection of nominal constant values of some parameter. If we have some initial condition that's close to, say, this blue one, initially we're going to have a good representation if we try to do some sort of phase reduction. But as we start to get further and further from the blue one, that representation is going to get worse and worse. And you might say, well, maybe now I'm just closer to this red periodic orbit, and I want to convert my coordinates in reference to this red one so that I'm close to this next one as well. So this is kind of a cartoon schematic of that general idea implemented with a discrete number of periodic orbits. But the idea of what I'm going to talk about is the same. We want to handle the reduction of dimensionality in terms of a continuous collection of periodic orbits so that we're never too far from any one of those individual orbits. So that's what I'm going to talk about in this mathematical approach and this derivation in the next couple slides. We're going to assume that we have some nominal system. The state is X, F gives the dynamics. P0 is a nominal collection of parameters which is potentially constant. It doesn't have to be changing, although it could be. And then U of t is some external input. So from a neuroscientific application, think this might be an external, DBS probe or something like that, that has the potential to change, influence the voltage behaviors and influence the spiking rates. So this is the actual system with the actual dynamics, and we're going to represent this in terms of a shadow system. So we're going to take this and think about it in a slightly different way. Instead of x dot is equal to x comma p0 as the nominal dynamics, we're going to have x dot is equal to f of x comma p as the nominal dynamics. So this is not necessarily the actual nominal parameter set, but it's going to allow us to represent the behavior in terms of some different limit cycles, as we saw in the previous slides. And then to that, we're going to add this effective input, which is just everything else so that this shadow system and the actual system dynamics are exactly the same. It's just in this case, UE is this effective input, which is different from the nominal input that's being applied at a given moment. So just some assumptions before we continue this derivation. We're going to assume that we have some continuous set of allowable parameters P. We're going to assume that each of them gives a stable periodic orbit, which is potentially different from all the other orbits. We're going to assume that for a constant value of P, we can represent the dynamics in a basis of reduced order phase amplitude coordinates. So here we're going to be using isostable coordinates, which represent level sets of the slowest decaying components of the Koopman operator, but you can use other amplitude coordinates if you want. So and this is a well-established strategy. It's just saying if we have a constant value of P, we can represent the dynamics near a given periodic orbit. We're going to also assume that the periodic orbits are continuously differentiable with respect to theta and our parameter P, and also that these reduced order coordinates theta and psi j are continuously differentiable with respect to x and P. So with that out of the way, we can change variables like we do in standard phase reduction to go from our state coordinates to our reduced order phase and amplitude coordinates. These depend on two variables now, so we get two things emerging out of this chain rule here. And the first of these components are easy to get. These are in fact what we get anyway from a standard phase amplitude reduction if we just have a constant value of P. This is that assumption I made earlier that says we can represent the behavior close to some nominal periodic orbit in terms of this phase amplitude reduction. You can see this looks similar to the standard phase reduction. We have some nominal value of the natural frequency. Here's a phase response curve multiplied by this effective input. And then we have some higher order terms here that give slightly more accurate corrections. The question becomes, how do we get these terms? And these are the ones that are going to tell us how do our phase and our amplitude coordinates change if we change the nominal parameter set, which effectively changes the nominal periodic orbit we're analyzing everything in reference to. So we have to figure out how these are going to change in time. And it turns out we can do this relatively straightforwardly, just taking some partial derivatives. So we take a look at the phase coordinate near the periodic orbit first. We do an asymptotic expansion up to second order accuracy. We have some nominal phase here. Here's the gradient of the phase, which is also the phase response curve, multiplied by the deviation between the state and the nominal periodic orbit itself. We have some second order terms. Here's the Hessian, and then we truncate finally after third order. We can take a partial derivative with respect to the individual parameters of this equation. Again, this is straightforward, recognizing that if you take the partial of the state itself with respect to a parameter, you're not actually changing the state of the system. Again, this is the shadow system that we're using to represent the state dynamics. You're not actually changing the state when you're changing the nominal parameter set. So if I take the partial of the state x with respect to pi, I'm going to get 0. If I take the partial of the underlying periodic orbit with respect to pi, that's going to be non-zero here. And everything else follows like you would expect when you take partial derivatives. We can do some simplifications to represent that result in terms of functions that we already know, some first order, some second order terms. And at the end of the day, we can combine and get equations that look like the partial of theta with respect to our parameters are equal to some function d of theta comma p. This is evaluated on a limit cycle. And then we have some higher order corrections, this linear combination of functions ek multiplied by our amplitude coordinates. And we can do a similar thing for all of the amplitude coordinates as well to get the partial of them with respect to the collection of parameters. And finally, we end up with this big mess of an equation, which is this adaptive phase amplitude reduction. Now, it looks like, there's a lot of terms here, but essentially, we're trying to figure out how the phase evolves in time, how the amplitude coordinates evolve in time. And we have the ability to change these nominal values of our parameters. And we can do this however we want, with the goal being that we want to keep the actual state close to the state on one of the limit cycles that we have available. And to do this, we have P dot showing up here and P dot showing up here. We can use this to try to keep, design GP appropriately to try to keep the amplitude coordinates small, so that if those coordinates are small, we're always close to one of the underlying periodic orbits, and we get a nice reduction that adequately reflects the dynamics. And then, of course, we can represent the actual state of the system in closed form in terms of the reduced order variables here. So a couple things to keep in mind. Again, that's a lot of equations, but the big takeaways from this strategy is that provided we can come up with a GP, again, this update rule for the adaptive parameters, as long as we can come up with something that allows us to keep all of those isostable coordinates, those amplitude coordinates small, in this case, order square root of epsilon, then we can give whatever input that we want and still get an accurate representation of the reduced order equations, accurate to order epsilon. This is in direct contrast with most standard phase reduction strategies, which generally require either the magnitude of the input to be small or the input to be varying slowly or something like that, which are generally restrictive conditions. In this case, we can use whatever magnitude input that we want and still get an accurate reduction. So this is going to allow us to approach problems that would otherwise be intractable. So here's a couple applications where this ends up being useful. We're going to think about the same circadian model. In this case, we're going to have a bunch of oscillators, 10 in this case, each with 4 separate variables, and they're coupled through this mean field value of D in through here. We also have this adaptive parameter. Again, think about this as a constant light input. And then we have this L of T term, which can be used to implement a light dark cycle or just any light input that you want to see how it changes the behavior. Using this adaptive reduction strategy, we can go from 40 states, 4 times 10 is 40 states, down to 5 states. So that's 1 phase, 3 amplitude coordinates, and 1 adaptive coordinate. And we end up with very nice results and better, in fact, than a lot of other standard phase-based reduction methods in terms of representing these dynamics. So here we have this black line is what if we do standard phase reduction on this. Red is the second order version, which is accurate to a little bit more accuracy. Extended phase reduction is has the explicit assumption that the input is changing slow enough to get a good reduction, and then this adaptive phase amplitude reduction. The blue one is the only one that works in this case. All of the other ones have this drift over time, and they really don't give a good representation of the overall dynamics. And of course, this gray line is the full model. You see the gray and the blue match pretty well. All the others, it's your best guess as to what's going to happen. So we have a model that does a good job of representing the dynamics of a high order model in a reduced order coordinate system. Now we can think about applying some of these strategies for control purposes and then use the resulting answers to see how well it works on the overall model. So in the second application, we're going to consider the same system. In this case, it's going to have 3,000 oscillators, so a lot more. There's going to be some heterogeneity, and there's going to be a little bit of noise in the system. But we can still do this adaptive phase amplitude reduction to get a reduced order model. We're going to come up with a control problem. In this case, if you're using a model that's based on circadian oscillations, you might think about, well, can I come up with a light avoidance or light seeking strategy to mitigate the effects of jet lag? So that's the problem that we're thinking about here. So we have some nominal value for an entraining stimulus, like a 24-hour light dark cycle that you all are entrained to in your home locations so that you can maintain appropriate sleep-wake cycle. We have this adaptive parameter L0 here, which is going to be used in this adaptive reduction, and delta L of T is going to be used to implement this light seeking or light avoidance strategy. And the rules of this optimal control formulation are going to be such that we start from a fully entrained solution. Then we're going to consider all possible stimuli that shift the phase appropriately in response to a change in the rapid travel across multiple time zones, for instance, to simulate jet lag, and try to find the one that minimizes the L2 norm of the effective energy. So this delta L squared, find the one that minimizes the control effort. We can solve this by applying a calculus of variations framework, finding what are the Lagrange multipliers, find the initial values of those Lagrange multipliers, and solve for the optimal inputs. We do that, and we get these results here. So in this figure, I'm showing the recovery time when we apply a couple different strategies to try to find a good delta L of t, a light-seeking or light avoidance strategy. This black line here is basically if you do nothing. If you shift your time zone, you shift your 24-hour light and dark cycle, and see how long it takes you to recover to that new, the new time-shifted 24-hour light and dark cycle. This red line here is using a phase amplitude reduction strategy. We use this in the control formulation. It's essentially phase reduction valid to first order accuracy. And as you can see here, nominally, if you don't do anything, sometimes you'll get a better result if you implement this strategy that's suggested that comes out of the optimal control formulation when you apply it to the real model, but sometimes you get a worse result here. It takes longer to recover. When we apply this adaptive reduction strategy to get those inputs out of that, we're able to relatively quickly re-entrain to this new target, fully entrained light-dark cycle. So similarly, in panels B and C here, we show those actual inputs that are predicted or that come out of using this optimal control strategy. We have two big pulses here for this one that doesn't work, two slightly smaller pulses for this adaptive reduction strategy, which does work for the plus 7 hour time advance. For the minus 10 hour time advance, we have different inputs. And we can see that when we apply this to our system, looking at model observables, here with this dashed line is this fully entrained reference. These initial conditions are minus 7 hours too slow, so we have to advance them by plus 7 hours. Applying this input allows you to get relatively quickly, when using the adaptive reduction framework, to the fully entrained solution that you want. The other ones don't work quite as well. And it's basically the same story for the minus 10 hour time delay as well. One interesting thing to fall out of this is, in something that's not mandated by the optimal control formulation at all, is that if you want to shift the phase of a large population of oscillators quickly, it seems to help to desynchronize them first. And we can see this in a number of different ways. And so this is for the application I showed previously. We're trying to respond to a time advance of plus 10 hours, so we have to shift the phase by that amount comparably. If we see traces of these model observables, time is equal to 0, we start our input, we have this big first pulse, and it really desynchronizes the phases of these oscillators. And in fact, it kind of destroys a lot of the oscillations initially, only to resynchronize to the new and correct time zone that we want. We can see this also in the raster plots and the effective locations, that the phase is equal to 0, a big desynchronization first, followed by a resynchronization. We can also see this looking at the Kuromoto order parameter in a rotating reference frame. Initially, we're all synchronized in our old time zone. We apply this input and we kind of go slowly through the middle of this rotating reference frame, which indicates desynchronization, to emerge at the correct re-entrained phase. This is for a plus hour time advance. Likewise, we have the same story for a minus 8 hour time delay. So initially we have this input which desynchronizes, and then we resynchronize to the new correct time zone, going through the middle here and re-emerging at the correct location with respect to the 24-hour light and dark cycle. So again, this isn't something that was mandated by the control strategy. This is just something that emerges for large shifts for a population of oscillators. And it might be something to look into further that perhaps might be universal. So some conclusions are these standard phase reduction techniques. They work really well when you're considering small magnitude inputs, when you stay very close to the underlying limit cycle. But they tend to fail if you apply large magnitude inputs, or if you're in a situation where you need a large magnitude input. This adaptive reduction strategy, where we're having some nominal, some adaptive parameter to try to keep you close to some underlying limit cycle, can be used to add maybe a couple extra states to your reduced order model without having to sacrifice accuracy if you're using very large magnitude inputs. And the resulting equations, as we've seen in the couple examples I've shown, remain analytically and numerically tractable in many applications. So just really briefly, some future and ongoing work. In most of the applications I showed today, in order to implement these adaptive reduction strategies, you need the model equations. In real life, usually you just have data. So it's important to be able to infer these types of reduced order equations from observable data in the case where you don't have the equations available. And there are some various approaches. One that looks promising is this machine learning based approach, essentially to get the right coefficients on the reduced order model. So that's something that's going on as we speak. Adaptive reduction strategies for arbitrary trajectories. One thing about these results is that it requires a stable periodic orbit, and you can't go through bifurcations. We assumed that there was a certain level of continuity, and if you go through a bifurcation, that continuity goes out the window. So being able to extend this to arbitrary trajectories would be useful if you need to consider situations like a transition through a Hopf bifurcation from an oscillating solution to a stable fixed point and vice versa. And of course, there are a lot of applications where this is useful: circadian, cardiological, and neurological applications to high-speed flows where you see oscillations, where these reduced order strategies are useful. Here's some references to some of the things that I've talked about today. And I'd be happy to answer any questions that you have at this point. Thank you.
All right. Feel free to applaud with the reaction. I have a question from Peter Thomas. Is there any evidence that the quantitative desynchronization of the oscillator during recovery from a large time shift is related to the qualitative feelings of discomfort experienced during jet lag in real life?
Yeah, I mean, that's a really excellent question. You know, in a lot of the literature for people who actually work, you know, on real life humans instead of models, the idea is always that there's some mismatch between the phase of the oscillation and the phase in your new time that's causing jet lag. But I think that it's likely that an unaccounted for factor is that there's some sort of mixing up of the you know, you have all sorts of bodily organs that are responding to inputs from the suprachiasmatic nucleus, and you're probably mixing up some of the relationships between the phase of oscillation between those individual things, which would be like an amplitude coordinate shift. And that's probably also causing some discomfort as well. And so, yeah, I think that's a great question that would probably, you know, require somebody who knows what they're talking about for you know, actual you know, the physiology and how people feel. But yeah, I think that's an unaccounted for thing as it currently stands.
Great. Thanks, Dan. Oh, looks like we got a couple more. So I'll go with Rachel's, and then Tony, you can unmute after this one, I guess. Rachel Nix asks, is there a general strategy for specifying G sub P to update P in the adaptive framework?
Yeah, that's a good question too. So if you have a low order system, so if you have one amplitude coordinate, one thing that you can do is set this GP here, which essentially sets P dot here, such that it kind of mimics this term in here. So multiply it by this term itself, and then times the isostable coordinate and times a negative constant. And so suddenly this acts like an exponential decay that's time varying. So you multiply it by this term, so you get a positive number, and then multiply by a negative constant. You kind of shift the exponential decay to larger values. That's one thing that works. You can also solve such that you cancel out this term here with the update rule. That only works under certain circumstances. But you know, the short story is if you have a couple coordinates, there are good ways to do it. If you have multiple coordinates, it's sort of, I don't have a good systematic answer for how to do that. You sort of have to do it on an application by application basis.
Thanks. And then Tony had a question.
Yeah, I prefer to do that speaking, because it's not easy to write down this. Hi, Dan. Nice talk. Yeah. Thank you.
Good to see you.
So I wanted to ask just the feeling. I mean, this adaptive method seems that improves some of the advantages of the extended method with phase and amplitude. Mm-hmm. And is that, I mean, the key point is this variable P that you introduced here. And also, I didn't understand, I think, the philosophy. You want to stay close to some P0 all the time, or you allow to the G to travel along across the P's?
Yeah, so thanks for the clarifying question. So the idea is, here's your nominal periodic orbit. But you've got all of these other orbits that may exist in the state space. And suppose you shift, give an input that shifts you in this direction. Now you're kind of in this region over here. You're far from this orbit, but maybe you're close to this orbit down here. So if you can sort of represent your system in terms of the dynamics around this orbit, and lump everything else and call that a perturbation, then you can get good, a good reduction that's close to your nominal orbit, so that you're not too far away from the nominal one that you're thinking about. So it allows you to kind of, in an intelligent way, update your effective limit cycle so that you stay, and hopefully to be able to stay close to at least one of these orbits here.
Okay, thank you. Yes, so it's like you are just trying to monitor which is the limit cycle you are following at each moment,
and not explicitly monitor, rather monitor in the sense that we keep the amplitude coordinates small. That's exactly right.
Yeah, I see. Thank you.
Right. And then one real quick question from Mustafa S.
Yes, thank you. Hi, Dan. So you compare your approach, the first order approach, second order approach, and the final this approach. And in some case, the second order approach gives, worse results than the first order. So I think the idea of increasing order is the increasing the accuracy. So why the second order gives worse?
Well, and that's a good question too. I mean, for both first and second order are based on asymptotic expansions about the periodic orbit. And once you go beyond those asymptotic expansions, all bets are off. And so the magnitude of the input is so large that it doesn't work for first order, it doesn't work for second order. And at that point, maybe you'll have something that's good and maybe you won't. But it's just illustrating that, maybe if you took it out to third, fourth, fifth, whatever order of expansion, maybe you'd be able to get something, although that even has its own limitations as well. But in this case, second order just doesn't work. Neither does first order.
Okay.
All right. Well, thanks again, Dan, and thanks for all the great questions.